So, good afternoon to everybody, and first of all, I would like to thank James for putting this wonderful conference together and for giving me the opportunity to be here, and also all the people involved in the organization. So, I'm from the University of Genova, and what I'm going to discuss is some work related again to quantum batteries, so still not over. The field of quantum battery is going on also this afternoon, but I'm not going to discuss and to repeat a lot of stuff already said by my colleagues. So only a few words. Again, quantum battery is one or a collection of two-level system or few-level system where we can put energy and use this energy later, okay? So in order to charge the batteries, to promote this object from the ground state to the excited state, we need some kind of external charge. People this morning discussed a lot about quantum way of charging the battery, so a cavity, a collection of additional two-level system, and so on. In this case, I will consider a simple case in which the charger is classical. So I'm not going to enter into dynamic of the charger. I only have the battery as some additional source that I use to promote the battery to the excited state. So how can I do this? The first simple things that came to my mind is that it's possible to use some kind of static drive. So I move from the Hamiltonian of the battery, let's keep it simple, a unique two-level system, so very simple, plus a coupling, so G times sigma x, which is typically a dipole coupling that is quite usual to assume. The energy stored into the battery is given by this, so I'm only considering the battery part, so this contribution, in order to see how much energy is stored into the battery, and then I can consider various figures of merit, such as the maximum energy that I can put into the battery, or the time that I need in order to charge. The maximum energy that I can put into the battery depends, crucially, on the intensity of the parameter, of the coupling. And strictly speaking, assuming static drive, I need infinite coupling in order to reach the maximum charge, the complete charging of the battery. So it's not doable experimentally. In very strong coupling, it's also useful in order to reduce the charging time. We need to reduce the charging time in order for the charging time to be slower with respect to the typical time scale associated to the relaxation of the battery, so the typical time scale that are not good for the performance of my battery. In order to go more into the direction of something that is doable, we can consider periodic or time-dependent drive. So adding time dependence into this, into my coupling, I can do something better in the sense that I can promote my two-level system closer to a perfect charging, 90-something% of the charging, in a very short time. But this, again, I can do by assuming, for general values, for quite general values of the parameter, assuming a coupling which is of the order of the level spacing. Again, this is not doable in experiment. This is out of range of the experiment. But okay. In experiment, there are already objects that works and that promote a quantum system from the ground state to the excited state. And these are the qubits that are in the quantum computer. And the qubit in the quantum computer typically works in this regime in which the coupling is lower with respect to the level spacing. So again, dipolar coupling, but the intensity is quite limited. This is true for superconducting qubit, but also quite in general also for other platforms like trapped ions. But if, in this case, under this condition, it is possible to realize the charging of the quantum battery, assuming a different form of my coupling, so of my external charging. So an envelope function times a cosine which is exactly on resonance with respect to the level spacing of the two-level system. Under this condition, it's possible to solve the problem exactly. Okay, exactly. In the rotating wave approximation, that works extremely well in this case. So, morally speaking, exactly. And the relevant parameter in order to describe the dynamic of the system is this object. So the integral of the envelope function from 0 to some given time, which assumed to be the measurement time. According to this, the energy that I can store in the quantum battery depends on theta, and is delta sin square of theta divided by 2. According to this, we are looking at objects that we can control. We, as a theoretician, we are able to realize some kind of, I don't know, in vitro experiment using the machine offered by IBM. So, the machine in IBM are transmon qubit, so an harmonic oscillator at cryogenic temperature. So if we consider the, let's say, dichotomy discussed this morning by Francesco, we are in the cold case, not in the hot case. Looking at the parameter, we have that this delta is 5 gigahertz, roughly speaking, and the machine of IBM and all the machine in quantum computer works in the qubit regime, so are able to address only the 0 and 1 state. Something that would be interesting that has been possible since 2020 is the possibility to control and to modify the pulse that we apply to the system. So basically control the form of this envelope function f of t. So with this ingredient, we are able to look at the optimal, in some sense, form of the drive that I have to put, control the parameter, control the time that I use in order to promote, to realize my pi pulse, basically. Before doing so, we need to calibrate the data because we have looked at what the machine is going to tell us. The machine basically, okay, in order to realize the measurement, we have a readout in the dispersive regime. Dispersive regime means that I have my transmon qubit coupled to an LC circuit. The typical energy scale are different. And by looking at the dynamic, or the modification of the frequency of the LC circuit, I can extract information about the behavior of the two-level system. So, these are the raw data extracted from the machine. So, for example, if I make the readout just after the initialization, I have this blob of blue point that I call the 0 area. If I realize, if I use, for the moment, a default pi pulse for the machine, I have this blob. Of course, it's not perfect. There are a red dot in the 0 area, and there are 0 dot in the 1 area because the machine is not precise. So there are errors. For every other pulse that I can imagine, I have this more complicated situation, two-lobe structure, in which I have the probability of being 0 and the probability of being in 1. I have to specify that I'm showing the picture of this harmonic machine. The term is now at the moment is no more available, and it's really the more stupid machine that we can have with IBM. So a single qubit that everyone uses for training, so really a stupid machine. And also, okay, what we can do, we need to basically change theta. Theta is our parameter. And theta is basically related to the integral of the Gaussian. And the Gaussian depends on two parameters. So it depends on the amplitude or depends on the width of the Gaussian. So if I fix the amplitude of the Gaussian, I can change the width of the Gaussian in order to change theta. If I do so, I observe that for small amplitude, basically I obtain some universal curve. But at high amplitude, there are deviations. These deviations are related to the fact that at high amplitude, my Gaussian is so narrow that I enter into the problem of the discretization of the signal. I cannot provide a continuous signal to my object, but a discrete signal. So I have this kind of ziggurat stuff that is not exactly a Gaussian, so I have to correct with respect to this. But I can proceed in another way, so fix the width at some fraction of the measurement time and change the amplitude. If I do so, the curve are more universal in some sense, so more robust. This process is more robust, and I observe some universality. This universality is, by the way, is different with respect to the behavior that I was expecting from a charging from zero. So there is some error associated. I'm not charging from 0 to 1. I'm charging from something a little bit different from 0 to something a little bit different from 1. So possible way to understand this is to consider error in the initialization or also thermal effect. We realize that thermal effects are not the main responsible of this, but error in the initialization can be the more can be the principal way of error. Okay. So we have fitted, considering this more general initial state, we have been able to realize this curve. Okay, in order to see the power, we consider lower and lower time. So we went down to the time up to the point in which the curve was not more universal. And we realized that the minimum time associated to this is around 120 nanoseconds. That means a charging time, if I look at the Gaussian, a charging time which is in the order of 80 nanoseconds. That can go down to 20 nanoseconds for more performant machines. Concerning comparison with experiment, this is a recent experiment that has been realized on a Q3, so a 3-level system, in which the first part of the curve is basically what we are doing now. And the charging time for them is 120 nanoseconds with basically the same level space. If I have 2 more minutes, no, I'm...
You're cutting into your questions now.
Okay. Okay. So in this paper, they identify 2 regimes. A regime in which there is a fast charging, but which is unstable, and a slow charging, which is stable. And they consider adiabatic dynamics. It's possible also for us, using IBM machine, to enter in the Q3 regime. So the IBM machine are transmon qubits, so multi-level system, and harmonic oscillator. So at the level of the hardware, there is no problem. There are problems at the level of the software that prevent for the majority of the machine to enter in the Q3 regime, because typically they don't want to play too much with the toys, basically. But if for some machine, it's possible to address also the transition from 1 to 2. And according to this, we realize 2 different kind of charging. One sequential charging, which is quite similar to, the one discussed in the previous experiment, so a 2-step charging, but also synchronizing the transition 0 to 1 and 1 to 2, with a simultaneous applying the pulse, is possible to directly to consider a direct transition from 0 to 2, which is faster and more stable with respect to what's shown in the previous experiment. So this is basically, as far as I know, the shorter, stable charging of a multi-level quantum battery based on superconductor. So I conclude the thanks to all the people involved in this project from the University of Geneva, from the CNRS, and from the CERN in Geneva, the Quantum Technology Initiative of the CERN in Geneva, that provide us the contact with the IBM machine. Okay, so thank you for your attention.
We have time for some questions. Does anyone have a burning question?
Comment, insult. Okay.
No questions? I mean, I have one. Given you're working with a single qubit, what's the difference between charging and a Rabi oscillation?
Okay, so basically there are, okay. They are Rabi oscillation.
Okay.
At the end, they are Rabi oscillation. The point is that instead of considering very precise, pay something at the level of the time in order to realize a good transition, a perfect transition from 0 to 1, we are more interested in do something fast without losing a lot of performance. So the figure of merit is a little bit different, but at the very end, we are working on, let's say, this kind of Rabi oscillation physics.